Okay, so we're going to start in chapter 15 talking about solutions. So the question I have posed to you right now is, why does a raw egg swell or shrink when placed in different solutions? Well, this is a biology question. So let's think back to last year when we were in biology and when we put our eggs in different solutions. So what ends up happening is the egg will shrink or swell because of a process known as osmosis. If the cell is hypertonic to a hypotonic solution, the water goes into the cell, making the cell grow or the egg grow. If the cell is hypotonic to a hypertonic solution, then the water will move out of the cell, creating it to shrink. And then that's how we get our eggs to shrink. And remember, if it's an isotonic solution, it stays the same amount of water in and out. And so that's the introduction to solutions. We already did this in biology when we shrunk our gummy bears and increased the size of them. So those are some things we already know. But what are some definitions we may not know? A solution is made of two or more substances. And so right here, you can see the two substances separated out. Those two substances are a solute, which is what dissolves, and a solvent, which is the solvent dissolves the solute. So water is a universal solvent. And so what are some characteristics that make that a solution? And so one of the characteristics that we see is that we have two substances that are now blended together in a homogeneous mixture. So they're evenly distributed throughout. They completely dissolved in one another. And so any two substances that will dissolve, a solute will dissolve in a solvent, that is a homogeneous mixture. The solute is always a substance that dissolves, and the solvent is the dissolving medium. Most of the time, the solvent is water. It's a universal solvent. However, it doesn't have to be. Alcohols can also be there, and that's pretty common for that one too. A solution can be made of solids, liquids, or gases, depending on the state of the solvent and the solute. And what they start in may not be what they end in. So here we go. We have a couple particles right here. We have a solute, a solvent, and they'll equal a solution. So remember, our solute is the part of the solution being dissolved, and the solvent is the solution that it is dissolving in. Okay? So the first one is an example, solid versus solid. A great example of this would be steel, would be the example. So the solvent would be iron, the solute would be carbon. If we look at a solid in a liquid, that would be like your dental amalgams. So that would be your solvent is your solid silver and your solute is mercury. If we look at having a opposite, a solid in a liquid, we would see like water would be our solvent. That would be like ocean water. And then solid sodium chloride would be our solute. That makes just normal ocean water. If we would do a liquid in a liquid, this would be something like, I don't know, vinegar. You have rubbing alcohol in your house. So your solvent is water in this case. And then your solute would be like the acetic acid to make vinegar or the isopropyl alcohol to make rubbing alcohol. And so those can go back and forth. If we would have a gas in a liquid, your solvent would be water, very common. And the other one is oxygen gas. And so this oxygen gas will actually dissolve in there, and that would be just like the water in your aquarium tanks that your fish breathe, or oceanic water would be another example. If we have a gas in a liquid, that would be, again, your solvent's water, and carbon dioxide would be the gas in the liquid. And you can actually see that in POP, carbonated water. Those are really good ones. Okay, gas and gas. This would be like nitrogen gas being the solvent because it's 78% of the atmosphere, and then oxygen gas being solute, which is 20%, and that would be the air we breathe. So those are some examples of that. So here's what we do know. If a solvent will dissolve, solute will dissolve in a solvent, it's considered to be soluble. If it doesn't dissolve, it's insoluble. Back to those rules that we had for double replacement reactions. Those will be helpful again. But oils are a little bit different. Oil is insoluble in vinegar, thus oil and vinegar are said to be immersibles. These are two liquids that are soluble in each other, such as antifreeze. These are said to be immersible. So again, two liquids that are soluble in each other are said to be immersible. Two liquids that are insoluble in each other are said to be immersible. So let's look at some more definitions. Let's classify the types of reaction or types of solutions that we have. So we have a saturated solution and an unsaturated solution. A saturated solution contains the maximum amount of particles it will have at a specific temperature. Temperature is really important because temperature can change saturation. So you probably know, like, if you put sugar in water and you dissolve it, it's fine. If you have too much, it just settles to the bottom. But if you heat it up, you can make candy from that. And then we have an unsaturated solution. This contains less of the atoms than what we can dissolve at a particular temperature. The temperature is really important because it can increase solubility. Pressure can also increase solubility too. So let's look at two things, a saturated fat and an unsaturated fat. And these are really comparing these two. So a saturated fat has all the hydrogen bonds it can possibly have. It is solid at room temperature. It's our normal butter that we'd find in the fridge. An unsaturated fatty acid has one less hydrogen bond, and it causes it to bend because of that. And it is liquid at room temperature. It will have an unsaturated fatty acid will have at least one double bond because it's missing a hydrogen. So it can't have a complete full bond. And so those would be two examples where one is saturated with hydrogen and one is unsaturated with hydrogen. And so those are two examples of saturation. Then we have what we call a supersaturated solution. Supersaturated solutions are unstable. So what can happen in a supersaturated solution, which is really, really cool, and we can kind of see here, if we would stick all of this into this, all the solute into this solvent, which is probably water, one of the things that can happen with a supersaturated solution is it contains more dissolved solute than saturated solution at the same temperature. To make a supersaturated solution, a saturated solution is formed at a high temperature and then cooled slowly. The slow cooling allows for the excess solute to remain undissolved in the solution at lower temperatures. A supersaturated solution is unstable if there's a tiny amount of solute added, such as what we call a seed crystal, one crystal. Then what can happen to this is that it will turn completely into ice. So it will completely crystallize. So one piece of crystal can go into that, and then it will completely crystallize. So an example of that right here, if you've seen this, a supersaturated solution of sodium acetate. So this is a one application solution. So basically there's a solute and solution in here, and then what do you do to activate it? You smack it, right? And then it actually starts to crystallize on the inside, which is kind of cool if you think about it. So we have talked about ionic compounds, knowing that ionic compounds are either soluble or insoluble. We've already gone through our solubility rules. We have them. And so they actually are great at having different solubility temperatures. So what that means is that they will dissolve. Most of them are soluble and will dissolve in water. There are some insoluble, and we have our solubility rules to tell us that. What happens here is our potassium, just as a reminder, our potassium and our permanganate are separated out in here. And so we can see that they're getting surrounded by water molecules. so that the positive sides and the negative sides. And so they're actually being separated within this solution. And we remember that there, a lot of times in this aqueous solution, they're going to create what we know as an electrolyte. So let's review what those are too. So we know that we have these ions in the solution. They're called electrolytes. This is when the positive and negative go onto opposite ends. This is way back in ionic bonding. So I want to review this a little bit. Remember, if it's a strong electrolyte, when it's dissolved in water, it will conduct electricity. If it's a weak electrolyte, it will not conduct electricity. Electrolytes are also important for our body, so that we can, conduct electricity and have nerve impulse. And you get cramps if you don't have enough electricity. And then we also have our non-electrolytes. These are things like sugar, ethanol. These are things that are not ionic compounds. They're usually covalent compounds. They will not conduct electricity. They do not conduct electrical impulses in our body. They do a much different process, such as sugar is used for cellular respiration to produce energy, but it doesn't conduct energy. So those are really important too. And so we can see with this, the non-electrolyte and electrolyte, and that we're going to move on from this. Our body really needs to maintain these electrolytes so that we can kind of understand how much we drink. So if you notice here, I have Gatorades and Propel and some things on there. So we know that, by the way, if you want to, you can make your own, but you don't have to make your own. We'll do something with this later. So we're giving you some solutions that you're going to be making. And so we are going to look at the amount of sugar and how that can change the concentration of the solution. And so if you look at this, your body is going to be making sugar. We will use the sugar. However, we do need those ionic compounds in order for it to function correctly. So let's talk about solubility in gases. This is specifically going to be Henry's law. I do have some problems that we're going to work through with Henry's law as well. Henry's law states that a given temperature, the solubility, or S, of a gas in a liquid is directly proportional to the pressure, P, of the gas of the liquid above. So a couple things that I want us to remember is that our pressure can be measured in ATMs, mmHg, and pascals and kilopascals. It's typically measured in ATMs and kPa, kilopascals, for this. But Henry's law is at a given temperature. Temperature is stable. We are not changing temperature for Henry's law. And so make sure this is the equation for Henry's law right here. You're also going to find it in the notes. The solubility of a gas in a liquid would be grams per liter is the definition for this. And pressure, we typically will measure in atmospheres, but we can also measure it in kPa, kilopascals, mmHg, millimeters of mercury, and Pa, pascals. Pascals is the SI unit, but it's not as commonly used as the other two. Okay, there's going to be a second video just working through his problems. I hope you enjoy.